let me welcome you now very officially to this experiment, because it is an experiment to have this kind of workshop. So it all started online when discussing to most of you. And at some point I was on holiday in Guadeloupe with my wife. We go there almost every year. We love it there. And so instead, I was thinking, instead of continuing this online interesting discussion and email and so on, why don't we meet? Many of you are meeting for the first time, so it's very nice. And yeah, let's see how this experiment goes. So I called it Varieties of Indeterminism. That's really the topic. And the title was involved from Carl Possi, who has a paper with this title. So what do I want to say? What is the main goal? Main goal is really meet, enjoy, discuss, disagree, listen, and show respect. By respect, be in space. It means be on time and address your talk to the others. So we don't want that philosophers are talking to philosophers and physicists to physicists, which would mean the quantum physicists to the quantum physicists and the quantum physicists. You should not talk to people who understand what you are saying. You should talk to those who don't share your jargon. One thing, since this is an invitation, it's open bar, which means at any time you can go and get a beer or wine or juice or coffee or cappuccino or whatever you want. Well, as long as the bar is open, it's all inclusive. Also, the excursion tomorrow, the next one about the excursion, is also all covered. I'll come back to that. I think this is already done. So if you have some food restriction, of course, you have to inform the hotel. And actually, here there's a mistake. It will not be a cheese fondue tomorrow, but a raclette. For most of you, you don't know the difference, so it doesn't really. Also cheese. Tomorrow, and now we know it will be tomorrow because the weather forecast is excellent for tomorrow. We go to this geisha. So it's very easy. So you take a bus and then you take a cable car. And then either you just look around and come back, or you walk. But if you walk, it's half an hour or maybe 40 minutes. So it's not a difficult exercise. So the departure of the bus is at 11:20 or 11:23 to be precise. So we should really meet downstairs, well, in front of the reception, let's say at 11:10 tomorrow. And then it's 5 minutes walking to the bus. And then it's 15 minutes with the bus. And everything is super easy. And it's beautiful, but it will be cold. So you don't need special shoes or things like that, except that it should be between -5 and -10 degrees. There will be sun, so it should be okay. And on the way back, you have choices where different. So of course you go back with the cable car, and then you have either a bus at 9 minutes past the hour, so after 3, after 4, and after 5, and there is one more bus in between at 3:30, I think. But so most likely we take maybe the bus which is after 3:30, there's one, and then 4:09. So 4:09 is probably our target. There's no target, and we don't need to go back all together. Everyone can do it as you want. And I think last year you walked back. How long was that?
Maximum 2 hours, but I think it was less.
But you walk from the top?
From the cable car.
You go down with the cable car and then we walk.
Yes, it's an easy one. It's an easy.
Asking, can we walk from the top? And I didn't find on Google, so I guess
no.
It must be possible, of course, obviously. But that's probably really much too much. But you can go down with the cable car and then walk. However, I don't think it's the nicest walk because there's still mud, so snow, but melted snow. So it's probably not the best time to walk back. While if you start from here, just go this direction and you enter the forest and you can walk, well, very far. And at some point you can turn left and you go back through the village, you turn right and you come this side. So there are plenty of beautiful walks around, but maybe not the one from the glacier. Okay. So yeah, thanks to everyone. Officially, my co-organizer, Flavio, Mark, and myself, but de facto it's Flavio who did 99%, can we say so? So sponsors, who is paying for that is my employer, Constructor University, and probably no one has ever heard of that. It's a small private university that collaborates, among others, with Geneva University. This map, that's, can you even have, oh, they don't have any poster here. So actually, Swiss map is the big project of mathematical physics, and they made, or they paid for this nice auditorium, seminar room at Geneva University. Okay, so let me also take the advantage of telling you a bit how I see this question in determinism. So you look at these beautiful waves in the sea, and you can ask as a physicist or philosopher, what is the best description of these waves? And of course, it depends what you mean best and so on. So best for predictions, obviously we want to do science, it must be predictions. But also, and that's something that I think many of my colleagues tend to forget, best for understanding. And what does understanding mean? For me, it means essentially being able to tell a story. So it has to be a meaningful story, a story that resonates, but also that makes predictions. And then you could say, okay, the best description is determinism. Classical mechanics, that's what we learn high school and universities, where everything is determined by the initial conditions. And the alternative would be the negation of determinism, which I know indeterminism. But then this one requires a kind of continuous creation of new information. And so this one will be really most of the discussions during these coming days. And my personal opinion, which I write here, don't get offended, but my opinion is that one has really to be seriously mad to believe that all these waves and all the details that you see here was all set up at the Big Bang. Although this is, of course, the official claim of classical mechanics. Is quantum relevant? After all, I'm a quantum physicist. So is quantum relevant here? And in some sense, obviously, yes, because between all these water molecules, you have interaction described in van der Waals process. But here we will have no one talking about hydrodynamics. We will have people talking more about cosmic dynamics or things like that. And there, of course, between galaxies, you don't have van der Waals interactions. And so somehow this drops. And I don't think, okay, a priori you may say there is no quantum randomness entering here. But that is, again, part of the debate. So is quantum relevant for cosmic dynamics? Okay, so that's the end of my little presentation. Enjoy the workshop, enjoy the discussions, debates, hopefully some little fights. No big ones, but small ones should be part of the fun. Okay, thank you very much. can be formulated in any using language. Is it fine?
I think they didn't hear until now. I think the microphone was off. Okay.
Okay, so sorry. Okay, so that is a good illustration why of the fact that real numbers contain infinite information. And so Gregory Shatter said that, so Gregory Shatter, probably you will know, it's a famous specialist of complexity, and he wrote that this way of representing or thinking of a real number is not only a correct one, but it's the only good one. It's the only good way of thinking. So when we think of a real number, we should have that picture in mind, because that's really what a typical real number is doing. So in particular, when we say let x0 be a real number corresponding to our initial condition, what we are really saying is let x0 be an infinite amount of information.
Can I just ask, can you just go back 1 second? I just want to ask a very simple question about,
Yeah.
Would you put typical in the second part of that definition? I mean,
So which is the second one here in?
no, the bottom, the only good way of thinking of a typical real number.
Yeah.
It should be, is the typical unlimited string of outcomes. Because you could have a string of outcomes that generates an atypical real number.
Yeah.
Could give you 3, 3, 3.
Of course, we probably.
So you need another typical in your definition.
I agree.
So how do you know that the outcome of a true random number generator isn't a computable? Well, it is a true real number.
Well, indeed, we assume that this is a true random number generator. Indeed, Gregory Shatter didn't draw this picture. He just said, let's use a true random number generator. Okay. Okay, so here now is a little argument that you may buy or not, but I think is a very natural one. And certainly that was actually my starting point with Flavio. So yeah, indeed, almost all of that is done in collaboration with Flavio. So let's consider finite volume of space. And here we just postulate that a finite volume, we assume that a finite volume can only contain finite information. I think it's a very natural assumption. It is an assumption. So herein, if I now put a little marble herein, for instance, the center of mass of this little marble cannot be described by a typical real number, because a typical real number contains infinite information, and then we would have infinite information in a finite volume. The position of this classical particle is not a real number, or more precisely, is not a typical real number. And here you may say, okay, but this is well known, this is a Bekenstein bound and all that. Yes, that is correct. But I don't think we need a quantum field theory and black holes. You know, we can just postulate that finite volumes don't contain infinite information. So typical real numbers, oh, here is one. That's the way I'm thinking actually about a typical real number. It starts with an integer, in this case it's 0. And then you get these strings of bits, digits here, coming out one after the other. And you can check that there is no structure. I really use the random number generator to generate that. Anyway, so it comes out, and you understand that after some time it will fill the screen. But that's not the end. Then it continues. And then it goes through the Earth. And then it continues. And at some point it will get out of the galaxy. And it continues. It continues forever. This is really a real number. Now, if there would be a real mathematician in the room, he would tell me, no, this is not a real number. A real number for a classical mathematician is the following. Now, pay attention. Don't look at me, look at the screen. Carefully. Cha! In 0 time, infinite information. That is a real number. 0 time, infinite information. That is what we have been trained to buy. Now, if we would fail that, we would probably not sit here because we would have failed our exams. But it's a very different presentation, having this digits coming one after the other, or as you may compute them, as they come about to exist, or according to classical mechanics, it's infinite information in zero time. So instead of indeterministic events happening as time passes, all the indeterminism is coded in the initial condition. Or you may say it also, instead of God playing dice as time passes, God played all the dice at the Big Bang and coded all the results in the initial condition. So here it really seems, so we start to understand this idea that it's really the mathematical language that forces us to speak of deterministic chaos. Now, if everything is given at once, of course, all the future is determined. It's all in the initial condition, and we have deterministic chaos. If you understand real numbers in my intuitive and so far very naive way, you see that the information is produced continuously as time passes. So something about intuitionistic mathematics now, but my way of presenting it will be very different from Karl Popper, which is mentioned here. So mathematical real numbers are not physically real, because in physics we don't have infinities. Or the short sentence that are slogan that I like here, real numbers are not really real. That's maybe the message you can try to remember. So you heard it. Karl Popper is saying, using this metaphor, there is no infinite helicopter allowing us to survey the whole terrain and to tell how things will look at the end of time. And here's something very important. How do real physicists do actually physics? Let's take as an example, people doing climate physics, certainly very important today. So these people like Tim Palmer, I think it's the same Tim Palmer that you cited. How do they do that? So they have huge computers and they have enormous amount of data. They kind of discretize the atmosphere and everything. And then they put all this data into their computers. And then, but it's finite, of course, their computer, even if it's a very large one, is a finite thing. And then we start to run the simulation. But because this, let's say, is a chaotic system, we soon will need additional digits that we didn't have at the beginning. Well, we just add. So we truncate the number to put them into the computer. And when we add stochastic reminder, we just add randomness in it. Because anyway, these typical real numbers, the digits are random. So we just do it, and we do it in real time. We don't do it in the initial condition just because it doesn't fit in the computer. So we just add it continuously. And this is a correct way of simulating, okay, the climate in this case. So I think actually the practical physicist, I hope you're doing similar things with, I'm not going to contradict me. But this is the way of doing it. So we a physicist, especially one that does computation, we never use a real number because it anyway doesn't fit in the computer, but he may need additional digits. Then he will just add random digits for his simulation. So somehow we're not using classical mathematics with real physicists. We are using something which is closer to intuitionistic mathematics. And we also already heard also, so statements about the future can be neither true nor false, but indeterminate. So in this sense, the law of the excluded middle does not hold. Here, I guess I have a bit a different opinion from Karl Popper. It's already said. So here we already start understanding whether Newton and classical mechanics is deterministic or not. It's not a scientific question. Also, it depends on this mathematical language. So the intuitionistic standpoint. So we already, Karl Popper wrote, we humans have finite memories, finite attention span, and finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter, as we already heard. Or another constructivist, famous constructivist, Bishop, he wrote, the classicist wishes to describe God's mathematics. The constructivist, the other side, to describe the mathematics of finite beings, man's mathematics for short. So constructive mathematics does not postulate a pre-existing universe with objects lying around waiting to be collected and grouped into sets like shells on a beach. Or Brouwer himself, so the father of intuitionism, he wrote, nature simply has not yet fully determined all objects. Well, this is already a bit similar to the uncertainty principle that we know from quantum mechanics. Now, you may get a bit worried if you listen to all that, except that yesterday Carl already told us that with intuitionism, you can also do computations and you can solve problems and you can prove theorems, maybe not always the same as the one we are used to, but it's a real mathematics with which you can really work and do proper mathematics. Okay. So here, try now to contrast classical and intuitionistic mathematics, especially about the continuum or the real numbers. So for the classical, I've illustrated with Hilbert, and for intuitionistic with Brouwer. So on the classical side, every real number is an individual completed entity. Boom, everything at once, infinite information is used. All digits are given at once. And the continuum is a collection of these individual points. So since we are individual points, you can take one out. 1/2, for instance, you can take out. It's a finite, it's a completed entity. So real numbers exist outside of time in some ideal Platonic world. In contrast, in intuitionistic mathematics, real numbers are processes that develop in time. I find that very fascinating because actually it's my intuition, these numbers, it's real numbers, you know. I think of them as really these digits coming one after the other. But of course, one after the other means that there is time. And that time could enter mathematics. I find that very fascinating. I know that in physics, I think we have a very poor understanding of time. And possibly this is partially due to the fact that we are using a language which is timeless. Difficult to talk about time with a timeless language. Try in English to talk about time, never using future and past. You know, it's very difficult. So digits are not all given at once. The continuum is a viscous collection. I'll come back to that, but essentially it is you cannot pick out one number because these numbers are not finished. Most of them are not yet finished. So you cannot pick them out. And time is essential. And at any instance of time, only finite information exists. Okay, so now let me give you my understanding of intuitionistic mathematics. It's not the same, exactly the same as Brouwer. Neither Brouwer nor Posey. So for me, we also will have these choice sequences. Well, the simplest way is this growing number. So each time step, you get this additional digit that gives you the next element of this choice sequence. So according to Brouwer, this is made by an idealized mathematician, but this is not physics. So let's change that and let's make the assumption that nature has the power to produce true randomness. So to produce new information. So we have something which I call here a natural random process that is going to output at each time step some random bits. And then at each, so this is what I just said, at each time, a natural random process outputs some random numbers, and these random numbers will be used as input for a computable function that will allow us from a previous element of this choice sequence to compute the next one. And I'll give examples. So this is just a computable function, and we'll impose that this is converging. So let's have some examples. The first example is the very simple one, where the last output, the last random bit that is produced by the natural random process is just added as the last bit of my number. So this is exactly, except here it's for bits instead of digits, but it's exactly what I had previously. And I call these, okay, the terminology is my invention, it's not due to Brouwer or Posse, but I call them these totally random numbers. Computable numbers, of course, they're also computable numbers. These ones are characterized by the fact that you only need finite up to k random numbers that will act like the seed of a pseudo random number generator. So then once you are past this time k, so you are given this finite information, then everything is determined. And of course, the standard example of a computable number is pi. And pi has moreover this nice feature that there is an algorithm, which is actually written here. And you see that the algorithm is clearly finite. So the bits may look random, but they're actually all hidden in the algorithm. And for this example of an algorithm computing pi, you can compute the nth hexadecimal of pi. It also means that you can compute any bit, even let's say the billionth bit, without computing the previous ones. So contrary to these totally random numbers, you don't need to wait to get every number one after the other. And let's say wait until the billionth if you want to know the value of the billionth bit. You can, with the algorithm, compute that billionth bit straight away without the need to compute the previous ones. And I think that's a nice illustration that the bits of pi don't come one after the other. You're already all there in the algorithm.
Where is the n? Is it that the sum goes to n? Or how do you?
No, here. So this is the algorithm that will compute pi exactly. It goes up to infinity.
Yes, but if I wanted.
Okay, so I didn't explain here how to do it.
Okay.
But maybe you. Okay, now it's a bit complicated. I don't want to go into that. But you can indeed use that. You see, you have this 1 over 16 to the power. So at some point, if you want only the kth nth bit, you don't need to compute the entire series here. You just need to compute one element of it. I'm not sure that this exists for all computable numbers, by the way. This is an open question. Okay, another example of an intuitionistic number, which we call with a value of finite information quantities, is very similar, but here we're going to take a majority vote on the k last outcomes of the natural random number process. So you build into your number some correlations. You can do that. Okay, let's go fast here. So this is very interesting number. It's similar to this number, I think delta, that Carl had yesterday. So we have a sequence that is going to oscillate around 1/2. So you see, if Rn is 0, this will be slightly larger than 1/2. If Rn is 1, it will be slightly smaller than 1/2. So it fluctuates around 1/2. However, the rule says, so this computation function says that this goes on, this fluctuation here, until by chance, the last half of the random bits all happen to have the same value. And okay, n is larger. And then if that happens, then it stops. It stays there, it sticks there, or it dies in my terminology. That's why I call it a mortal number. And so here you see that this may go on forever, or it may stop at some point. And because the probability of dying, terminating, decreases exponentially, there is an a priori probability that the sequence goes on forever. So it could go on forever, it could stop. And clearly, before it stops, you don't know. It is undetermined.
So it stops or it becomes all the same?
Yeah, or it stops in the sense it settles to value it and remains at this value, which is the same as lost. Okay, it's similar. Yeah. Okay, so the proposition alpha smaller than 1/2 is neither true nor false, but indeterminate as long as the process didn't die. Okay, autonomous number. I just want to say you could also have that, and at least team will recognize pictures of collapse models like GRW or my quantum state diffusion models. And it's actually, if you go into the equations, is really the same equation. So you see some connection between these kind of quantum models and what I call here autonomous numbers. Then you also have logic, and I think I need to go a bit fast here because we also heard a lot about that yesterday. So you have this indeterminism. Okay, I just said that. This is similar, in my opinion, to this statement, it will rain in exactly 1 year time at Piccadilly Circus, which is presently indeterminate. Now, the absence of the law of the excluded middle implies that some theorems that we know how to prove in classical mechanics using the law of the excluded middle, so we prove them by contradiction, or in a way, in a non-constructive way, these proofs will no longer be valid. So this is surprising. But again, in an indeterministic world, it makes plenty of sense that you cannot prove non-constructively the existence of some mathematical objects. Again, Brauer said, so excluded middle fails because the world is not determinate. The proof about it are. We're not in this intuitionistic mathematics, we are not discretizing time or space or anything. It's somehow discretized, but the discretization becomes thinner and thinner as time passes. So it's not a given fixed discretization. So there is a continuum. So again, here, let me go a bit fast. And this we already heard yesterday. So all total functions are continuous. Here, maybe just let me emphasize on this example about Gisin's theorem, because this is very important in quantum mechanics. So the proof that Gisin gave of his own theorem does not hold intuitionistically. So for a time, people were wondering whether this theorem is maybe not correct in intuitionistic mathematics. However, this person, and actually also Itmar Pitowski, then later proved that Gisin's theorem is actually, can indeed be constructively proven, but using a different technique. So some theorems will no longer hold, some new theorems will hold, and some theorems are valid in both classical and intuitionistic mathematics, but might require different proof techniques. You also have arithmetics. Let me jump over that. Okay, so here I like this table because, you know, here is my intuition about physics, and here is intuitionistic mathematics. So for instance, in my intuition here, past, present, and future are not all given at once. The future is open particular. So digits of real numbers are not all given at once. Time passes. Numbers are processes. Indeterminism. Number contains finite information. The present is fake. Okay, here I didn't elaborate on that. The continuum is viscous. You cannot take out one point of time. The future is open, no law of the excluded middle, becoming, choice sequences, experiencing, intuitionism. Okay, so once you have an indeterministic physics, so far we have now indeterministic classical physics, what can you do? Well, I guess there are at least two ways. One is to search for supplementary variables, famous hidden variable that we all know about, such that randomness is now purely epistemic. Or the second one would be to really accept rest potential. So let's start with supplementary variables to my classical indeterministic physics. So as we said, instead of God playing dice when potentialities become actual, God played all dice at the initial condition, at the initial time, and coded all results in the initial condition. So instead of new bits in this series gaining determined value, the bits gain relevance. So postulating that the initial condition of all classical dynamical systems are faithfully described by mathematical real numbers is an elegant way of adding all future results, for instance, of chaotic systems, while making sure that they remain inaccessible for long enough a time. So the real numbers, the standard classical real numbers, are the hidden variables of classical mechanics. No, we use these numbers all the time, but actually, of course, the very far down the series digits are hidden. And these are the hidden variables of classical mechanics. So we face a choice. Either the fact that at present certain things happen and others do not is interpreted as revealing retroactively information about long past initial conditions, or else we understand the present as a result of indeterminate reality and the future is open. So obviously I prefer the later one. And here, the fact is that most physicists, almost all physicists, accept real numbers without even noticing that these are hidden variables, while the same physicists simultaneously reject Bohmian position as unnecessary. So you should be consistent. So either you accept real numbers, but then there is no reason to reject Bohmian positions, or you reject Bohmian positions, but then you should also reject real numbers. So the second alternative, so let's now forget about hidden variable and accept rest potential at the same level as rest extension, and try to understand how we go now from indeterminacy to indeterminism. Because indeed, indeterminism, in the sense that there would be a causal chain that starts out of nowhere, out of the blue, that would be kind of magical. No? This is probably a kind of argument against indeterminism. Things cannot happen without a cause. But on the other side, that a physical system has a state which is not yet fully determined, like the real numbers. This, to me at least, sounds very physical. And indeed, our world is full of indeterminacy. And now, as time passes, again, time is essential, new information reduces the indeterminacy. And now, so you have your indeterminacy that may grow if it is a chaotic system, but at some point, the new information will decide that you took, let's say, the left path in the fork or the right path. So it leads to indeterminism. But here, indeterminism does not come out of the blue. It is certainly not acausal. Simply some potentialities get excluded. So let's come to this main motivation, bring classical closer to quantum. So now, in this view, with this intuitionistic mathematics, both can be seen as indeterministic. And hence, there is a measurement problem, which is very well known in quantum. But now, and you may say this is a step in the wrong direction, but I think it's an interesting step anyway. We also have a measurement problem in classical mechanics. We wrote that with Flavio already years ago now. And how are you going to, so the question is really, when do potentialities become actual, and what triggers this change from potentialities to actuality? So what reduces indeterminacy? And there are several possibilities. I'm not going to solve the measurement problem today, but it could be spontaneous, as in GRW, or also the way I presented this intuitionistic mathematics. Just nature produces these random bits, and this continuous process continuously reduces indeterminacy. It could be also triggered by higher order demand. That's a bit the Copenhagen view. I know it's a bit vague, but the idea is that, you know, there's this big classical apparatus that forces the quantum system to make up its mind in some sense. It's a bit vague, but I think it's not a hopeless potential solution. And then there are hidden variables, obviously. And hidden variables could be the real numbers, that's the ones that we know very well, or the Bohmian positions, if we think quantum mechanically. Also, the many world of Lev Weidmann and many others could now also be applied to classical mechanics, because you could say that each time this, what I call this random number process outputs a bit, maybe it outputs both bits, and both futures realize in parallel, whatever that exactly means. So somehow this many world is really a consequence of indeterminism. Okay, and what about non-locality? Well, I think that there is a part, some of non-locality, not all, but some of non-locality that can also be seen in classical mechanics. Let's think here, we have a particle with some indeterminacy, and we have a beam speed, or we have a fork in the path. So this is going to, you know, two locations now. But now let's suppose that either on one side or the other side, some new information or some top-down causation will force to get this particle to get better localized. Then, if it gets better localized, in this case on the left, you have a form of non-locality because what was there, indeterminate, now gets determinate to be just vacuum. So something disappears somewhere. And this is, of course, this is not Bell non-locality, but this is a form of non-locality that actually this picture is very much like a photon on a beam splitter that already Bernard Einstein with two detectors, one detector detect the photon and then force the other one to vanish. You can even go now to pairs of particles, classical particles, that have this blue indeterminacy. But let's suppose that the relative indeterminacy is way lower. So the green here shows the relative indeterminacy. Let's suppose this is position. So the position of this particle is not better determined than that. Same here, but the relative distance might be better determined than the position of each of them. And now if something here again, you have this particle to gain some determinacy, so reduces the indeterminacy, it could go like that. But now because the relative distance is better determined, if I reduce the indeterminacy here, it will necessarily also reduce the indeterminacy here. And this will go on until here I get below this green relative indeterminacy. Then this one will no longer be affected. So this one will only get reduced, its indeterminacy will only get reduced down to the relative indeterminacy. So here again, we have something that looks very much like non-locality, which is non-locality in some sense, although clearly not Bell non-locality. Indeed, what is now the difference between classical and quantum? I'm not saying it's the same, because there remains something which is only quantum, namely, it's only quantum that has incompatible physical quantities, the famous non-commuting operators or observables. And indeed, it's also only when we introduce these incompatible physical quantities that Planck's constant enters. And you need incompatible measurements to violate the Bell inequality. So as long as you don't have these incompatible measurements, you cannot violate Bell inequality. So in my indeterministic classical mechanics, you don't violate Bell. You need, let's say, H bar to violate Bell, because H bar is the only thing that guarantees that you have incompatible measurements. Okay, so I'm coming to the end. So as I already said many times, so the mathematical language we speak when talking physics impacts our worldview, deterministic or not. Classical real numbers are the hidden variables of classical mechanics. And somehow classical mathematics assumes a view from the end of time. Of course, if I wait until the end, of course, it's going to take an infinite long time. But at the end of time, somehow, then everything has settled. And then I have classical mathematics, and hence, obviously, also everything, all the future has happened, and then things, there's no indeterminacy left. Okay, I added here this. Classical mathematics is reasonably inefficient to talk about physics. Now, we always talk about the unreasonable efficiency of mathematics, but I think it's wrong. Actually, mathematics is terribly inefficient to talk about time. Okay, and okay, these are the last papers here with Flavio. Try to also connect that to relativity. Okay, nice ideas, but I would say not completely complete. And the open path that Carl also mentioned yesterday, we also have a paper on that one. Okay, I think I'll stop here. Thank you very much.
Questions? Listen.
I just want to situate the whole project in the bigger picture. So as you started the mathematics in language which narrate the story about nature, as any language could be more or less adequate to express underlying nature. So your project essentially is, and so there are also two things about mathematics as a language of nature we can ask about. Which pieces of mathematics express something physical, because not everything in mathematics, of course, expresses something physical, and what kind of mathematics is adequate to express nature. So so what you want to say, given that the nature is deterministic, we are using a wrong mathematics to
Given the nature is indeterminate.
indeterministic, yes. Given that the nature is indeterministic, we are using a wrong mathematics to express indeterminism. And the wrong mathematics is not just pieces of mathematics, but some kind of fundamental view how we view mathematics itself. Right? It's sort of really going to foundations of mathematics rather than just some pieces of mathematics that are inadequate to express a story about the nature we live in. So that's your motivation to switch to intuitionist mathematics.
Yes, so absolutely. I think you said it very nicely. I fully agree. I would just add one thing. My motivation is exactly the one you said. But now, I mean, I have also to admit that all what I did is to show that classical mechanics can both be viewed as deterministic and indeterministic. I didn't prove that classical mechanics is indeterministic. But indeed, my hidden, not very hidden, agenda is to go towards indeterminism.
Okay, that's also true. So even you went a step further. It's not that just quantum mechanics or new physics has to use new mathematics or intuitionist mathematics. Intuitionist mathematics is good language, good tool to describe even classical physics, because classical physics has all these elements that quantum mechanics has as well, namely indeterminism, or, other things you mentioned. So that's the large, I just want to look at the forest, right, before we go into little pieces.
Oh, thank you. It's absolutely correct. I'm happy you got it. Yes, Tim?
So let me ask, this is sort of connected to this. If we separate physical reality from some mathematical gadget that's being used to represent it, as I understand it, and I can understand the motivation. On the physical side, you want to be a strict finiteness. I just don't think there's neither infinite divisibility nor infinite extent, right? And I don't exactly share it, but I understand that someone might say on that side, I don't want anything as it were infinite at all. But then I don't quite understand, why aren't you tempted to do something like, say, let's just take space-time structure. Yeah, put it on a lattice, make it all finite, make it, I don't know, close it maybe so it doesn't go on infinitely. But you said you didn't want to do that, or you wanted, if it's a lattice, it kind of keeps getting finer or something like that. But what's the motivation for you to want to do that? Why not just say, no, it's just finite, go down to Planck scale. The actual initial condition of the universe is finitely specifiable. Why isn't that more in tune with what's motivating you to do this, rather than what you're kind of trying to do is recover a whole lot of what looks like real analysis, but isn't really, which is what's forcing you to go intuitionist.
Yeah, I understand what you're saying. What I wish, in addition to this finiteness, is time. And as time passes, something has to happen. And what happens in this view is really that this grid becomes thinner and thinner.
I know that's your view. I'm wondering why
Because if not, I don't have time, then we have no time at all. If I have just a finite grid, and again, everything is deterministic in a different state space. But again, it would all be given at once. And I like the idea that things happen as time passes.
I'll try one more. Suppose I just make it finite, I have a fixed grid spacing, as it were. I have finite space, I have finite time, everything's discrete. I do some physics on that. It could be either deterministic or indeterministic. The equations could either be deterministic equations or stochastic. I could do it either way. But I wouldn't need to keep refining the grid size. I'm not sure why. I understand that's part of your picture. I'm just trying to understand why you think that particular thing has to happen, that the grid size changes.
Again, that's especially in chaotic dynamical systems. If you have a finite grid, at some point you will fall in between the lines somehow. And then you're changing probably some predictions. So I don't know exactly. There is also probably a need. You may anyway say that classical mechanics is going to fail if you go to too small scales. Okay, I agree that a fixed. Now I see your screen. Yeah, I agree that this is an alternative to have everything finite on a fixed grid, maybe then with stochastic equations, evolution equations. It's an alternative. It's not the one which I prefer, but
Okay, that's, I'm just wondering, I see that, okay.